By the end of this video, you will understand the relationship between frequency, wavelength, and all the properties of electromagnetic radiation, and be able to do some calculations that relate frequency, wavelength to the energy of a wave. So, how this all began, or how this seems to need to get started, is whenever we have white light, like from the sun, that white light, when it passes through a prism, can be split. That's a property of light that we have seen and witnessed. Why does that do that? Well, it turns out that white light is composed of all of these different colors of light. Okay? So white light is made up of the rainbow colors. Now, I say rainbow because how does a rainbow actually work? Well, a raindrop actually acts as one of these crazy little prism things. Okay? And so when light from the sun kind of goes through a raindrop, what happens is it separates the white light into rainbows, and that's what we see in the sky. Okay, so rainbows have been witnessed for since the beginning of time. So, this is kind of why rainbows exist in nature. But there's more to it than just pretty rainbows in the sky, and so that's what we're going to get into. Okay, now, in order for us to understand light and energy, maybe it would be good if we decided to talk a little bit about sound. Okay, now, sound is similar to light in terms of how it works. You end up having a wave, okay, that is created, in this case, in a guitar, by plucking a string. Now, when you just strum a guitar without touching any of the frets, the guitar makes a certain sound. And the reason why it makes a certain sound is because it has a wavelength of maybe something like that. Okay? Now, if you fret the guitar, if you touch the frets here and prevent the wave from going from this end all the way out to wherever the pin is, now you're talking about fretting it to here. Well, you've changed its wavelength, you've changed the length that it is able to vibrate. And by doing that, it changes the sound. And on down the line, depending on where you press the fret, or touch the fret, it changes the sound of the guitar. Well, light is the same way. As the energy, or as you change the wavelength of light, you change the other properties of it as well. You change its frequency and its energy. So that's where we're going with this. Okay, so there are properties of wavelengths that I think we need to know. Okay, wavelength is the length of one wave, from the top of a wave to the top of the next wave. And that is symbolized with this Greek letter. That is called a lambda. Okay, lambda. Okay, I draw it kind of like this. It's kind of like a capital T that has fallen over. We measure that in length units of length, so we measure those in meters. Now, another property of a wave is a frequency. How many waves pass a point during a certain period of time? Okay, and so that is symbolized usually by this Greek letter nu. It's spelled nu, but it's pronounced like not old, but new, right? Okay, but it's a Greek letter, and when I write it, I kind of write it like this sometimes. So you'll see me write it kind of like a snake, or maybe a funny looking bird, like third graders draw a bird. Okay, and its unit is 1/seconds, or hertz. Okay, these are the same thing. Sometimes it's just easier to say hertz as opposed to 1/seconds. Okay, and the other property of a wave is amplitude. It's how tall a wave is. Okay, now we are going to talk a little bit about amplitude, but typically amplitude doesn't play much of a role in what we do in this in chemistry. Okay, so notice what just happened here, though, that this changed, okay, to F. Sometimes you will see this as F because frequency is F, okay? And so, but I'm always going to use nu, but please don't get confused just because you see an F pop up. Okay, so here's a wave, okay? It's a wave of yellow light, and we know its properties, okay? Crest is on the top of the wave, the trough is on the bottom, the origin is here. So that is the wavelength, okay? And the wavelength is measured from usually it's measured from crest to crest, but it can be measured just like it showed there, but we got rid of it. It can be measured from any point to any point to the same point on the next wave. Now, the reason why we use crest to crest because it's easy to go crest to crest. When we're going any point to the same point on the next wave, sometimes we get confused and we're like, oh, it's right there. But unfortunately, this one's going down, and so we have to go find the place where it's going down. So it's just easier if we take the wavelength from crest to crest. It's standardized. And the amplitude here is the height of the wave. Okay, so from the origin, which the computer kind of got rid of, to the top. Okay, so now if we change the amplitude, notice that the wavelength here is the same. Okay, what this means and what this changes, it doesn't change the color of the wavelength, but what it does is it changes the intensity. You may equate this to brightness. Okay, so if the amplitude is bigger, you're going to have a brighter wave, and I think that this is kind of shown here because this is a little bit thicker than this. Okay, so it's tough to see. But let's change something a little bit better. This changes the wavelength. Notice here the amplitude is the same, okay, or at least it's trying to represent it being the same. But if we draw a picture of the wavelength is shorter. By changing the wavelength of the light, we have changed its color. Okay, so now by changing its wavelength, we've also changed its frequency because it's a shorter wavelength, more can pass a given point in a second. And so the properties of the waves determine those things. Like in a sound wave, it determines the sound. Well, in light waves, the color of the light is dependent on these things. So let's talk a little bit about frequency. So here we are linearly representing what 1 second looks like. Okay, so we're going to count how many times a wave happens in 1 second. Okay, so here what happens is we get four waves happening over this 1 second. Okay, now let's do another wave. Notice what's happening here. Okay, the wavelength is getting smaller, and because the wavelength is smaller, that allows more waves to pass by the point in 1 second. So that means that in this case it's 12 cycles per second, or 12 waves per second. See, that's the per second, which whenever it's per second, that's hertz. Okay, now we can get really small, and here we have 36 cycles, or 36 waves per second, or 36 hertz. Okay, now again, we see this in sound too. The sound, as it has a bigger wavelength, makes a different noise, the guitar, but instead of a noise, now we're talking about a color. Okay, and so there's our little doggy listening to this thing. Okay, you may have heard about frequency when we're talking about radios. Okay, radios you turn into certain frequency. Now we don't see AM much anymore, although my favorite talk radio station is AM 610, which has sports talk, ESPN radio. But what happens is if you have a pattern of sound, what we can do is we can either do AM, we can amplitude modulate that sound. See what happens. So this, as this goes up, the height of the wave goes up, and as this goes down, it goes down. And so we are changing the amplitude of the wave based on what the sound pattern is that we want to hear. That's amplitude modulated. And if we can modulate the amplitude, we could also modulate the frequency. Okay, and so here, this one's a little harder to see. So as this goes up, you can see that the frequency is getting, the frequency is getting kind of smaller, right? Because it's getting, the wavelength is getting bigger. Okay, and then as this goes down, the wavelength is getting smaller until it gets to the bottom point, and this wavelength is the smallest here, right? And then it goes up, the wavelength gets broader, and so that process is called frequency modulated, and that's where AM and FM radio comes from. Okay, and so I'll skip over that. And so here is the breadth of all the different parts of what we call the electromagnetic spectrum. Okay, the electromagnetic spectrum is split into 7 regions. From here, gamma rays, all the way down to radio waves. Okay, and notice the smallest part of the electromagnetic spectrum is the part of the spectrum that we can see. Okay, and so there's a whole boatload of stuff out there that's happening that we can't really experience with our eyes. And that's kind of interesting. Actually, in astronomy, only one small part of astronomy deals with looking here, visible light astronomy. That's the kind of astronomy that you're used to. You know, you take your telescope and you look up through and you're like, hey, look, telescope, woo, look through the telescope and you see a star out here. Okay, but stars not only give off visible light, but they're also giving off radio waves and microwaves, and you can look at stars using radio waves and microwaves and gamma rays. Okay, and you can see the relationship here as the wavelength, and so this is the wavelength. Let me get rid of some of this here. Okay, as the wavelength changes, okay, and so the wavelength here is getting bigger. Radio waves have really big waves in meters. Look, this is 10 to the first meters. 10 to the first is 10 meters, and it goes on. You can have a wave, or a radio wavelength that is, you know, like 300 meters, which is huge. Notice what happens to the frequency. As the wavelength increases, the frequency decreases. Okay, and so that's the relationship that I want you to keep in mind. Okay, so we're going to explore that relationship in the next video.